Welcome to the lecture series on vitamins and nutrition. Today we are going to look at this water soluble vitamin pyridoxine, which we have already started in the previous session. We have looked at various aspects concerned with the structure, the historical background. We even started with the metabolic role of pyridoxine. So I want you to get back to this slide, refresh you with this particular structure even as we proceed discussing the metabolic role. And today we will emphasize more on the metabolic role, what we have already seen earlier. In addition to that, we will also look at deficiency conditions connected with pyridoxine. See, this particular compound, as I've told you, is a fundamental compound with the pyridine ring, and the active form, what we call it as the pyridoxal 5-phosphate. And these are the reactions that they catalyze: transamination, deamination, decarboxylation, and condensation. So when you say transamination, you transfer an amino group from one compound to the other compound. In deamination, you remove the amino group, and in decarboxylation, you remove the carboxyl group, especially the carboxylic group present in the carboxylic acid, and you remove it in the form of a carbon dioxide. And in condensation, you basically bridge two different compounds by letting out a water. So these are the reactions which are catalyzed by variety of enzymes, and all these enzymes basically use PLP as a cofactor. Now we have already seen this, and I want you to be aware of what is the role of this particular compound, especially the aldehyde group of the pyridoxal. It actually forms an imine. In other words, it could be, I would say, the Schiff space formation. So the Schiff space formation, it acts like a kind of a Schiff space where nitrogen acts like a sink, and this helps in the withdrawing process for decarboxylation and deamination. So you see there as a Schiff space, it forms an internal aldimine. So internal aldimine with the epsilon amino group of a specific lysine group of the aminotransferase enzymes. So all transferase enzymes, you find the aldehyde group acting like a Schiff space. Now as you go further, you would get to know the variety of reactions that they catalyze. So this reaction we have seen already, transamination, and in the phenylalanine metabolism, how tyrosine transaminase uses PLP, pyridoxal 5-phosphate, in transferring the amino group, and here you have the amino group is being removed, and here you have a carboxyl group. So this is hydroxyphenyl pyruvic acid. Now when you go further, when you look at decarboxylation, in the previous slide you have seen how the amino group has been removed, and in this you look at the decarboxylation where the carbon dioxide is removed from the carboxylic acid group. So especially L-dopa and dopamine are neurotransmitters, and they play a very vital role in the normal metabolic function of the brain and in the neuronal connection, in the synaptic junction between the neurons. So dopamine and L-dopa. So you see there, dopamine basically conversion of levodopa into dopamine. So levodopa is the precursor. So in Parkinson's disease, normally there is depletion of dopamine, and levodopa will get converted into dopamine, and this facilitates the conversion of excitatory neurotransmitter glutamate to the inhibitory neurotransmitter GABA. Now here you find dihydroxyphenylalanine. So dihydroxyphenylalanine, basically that's the dopa. So where you remove this, and then you have dopamine as a neurotransmitter. Now this reaction we have seen, we'll quickly go through. This is something special. In this case, in the PLP, the phosphate group plays a very interesting role. So you see there the phosphate group on the PLP actually participates in the reaction. So far in the previous reactions we have seen the aldehyde group taking the lead role. Now in this case, the phosphate group helps in splitting the glycogen to give you glucose 1-phosphate, and glycogen being broken down, this reaction is called glycogenolysis to release glucose. So whenever a body is under stress and some of the stress hormones like epinephrine or adrenaline is released, it initiates for muscular movement, especially skeletal muscle movement, breaking down of glycogen to release energy, because muscle glycogen is broken down for muscular activity, and this is all initiated by the stress hormone epinephrine or adrenaline. Now you look here how this reaction proceeds. So you have the acid catalysis, so the proton donor and the proton acceptor. Okay, so how the glucose is being split and how energy is being released. So here we have heterolytic bond cleavage. As you see over there, it's a very essential part as part of the amino acid metabolism. So here you have the enzyme bound structure, the active site component, and here you have a pyridoxal, and you see there the amino acid is present, and now the pyridoxal interacts with the amino acid. So here you have PLP providing a stabilizing role, and thereby you are able to cleave. It acts like a kind of an electron sink. Eventually the amino group is removed. So this entire process is all about the amino group forms a bridge with the group over here, the pyridoxalamine group over here. So the amino group interacts with the aldehyde group. So you see there the amino group interacting with the aldehyde group, and this electron acting like a kind of an electron sink helps in pulling this amino group away, and once the amino group is pulled away, the resulting amino acid leaves as a keto acid. So you see there, this is how the reaction of heterolytic bond cleavage happens, and in this case you definitely find there is a Schiff space based mechanism happening. So here we go. So the reaction is repeated, and you know pyruvic acid is a very important metabolite, and it's a key energy molecule which enters citric acid cycle. So you know how this proceeds is how the active site of the enzyme and then the PLP, and how the amino acids are decarboxylated and removed, and eventually you also remove the amino group. So this is how a clean way you could have keto acid derived from a amino acid. So here we have one more reaction. So this is the classical reaction what I have explained earlier. Here you have the first half would be decarboxylation and the second half would be transamination. So the lysine residue in the transferase enzymes actually interacts with the pyridoxine. Okay, so you see there how this proceeds to the formation of quinonoid through external aldemine. So here you have the external aldemine. So this external aldemine is what we mean by the Schiff space. Here you proceed further by a quinonoid structure which is stabilized, and finally we have ketimine. Then the reaction proceeds further. So once you have a alpha keto acid, again the reaction proceeds, and finally you look at here you have two-step reaction with the same mechanism where you have a decarboxylation happening and you also have a transamination. So the mechanism is basically, it's not like simultaneously two different reactions are happening, but rather you can take it this way. The decarboxylation is one part of the reaction catalyzed by PLP. The other part is basically the transamination. So both proceed with the quinonoid formation, with the aldemine formation, and here you have a alpha keto acid, how the amino group is transferred, okay, and how the carboxylic group is reversed. So here we go, one more amino acid, tryptophan, which is getting converted to 5-hydroxytryptophan, and this 5-hydroxytryptophan gets decarboxylated to give you 5-hydroxytryptamine. So here you see decarboxylase using TLP as a cofactor. So we earlier saw dopamine being formed, and here you see serotonin being formed. So dopamine and serotonin both are concerned with the mood of an individual. So all the mood elevations and probably the mood swings associated with pyridoxine deficiency can be attributed directly to the role played in the neurotransmitter biosynthesis. So suppose if we do not have adequate amount of pyridoxine, probably the amount of serotonin and dopamine being released would drastically be affected, and this exactly leads to the kind of neurologic symptoms that you normally find with people suffering from pyridoxine deficiency. Now we look at in detail various metabolic disorders which result from vitamin B6 deficiency. So we are going to go one by one. The first one is we say the isolated B6 deficiency is uncommon. Yes, it's true, because we somehow get this particular vitamin, and a prolonged deprivation, as I have been repeating this phrase for many times, especially the B complex vitamin will have a combined effect of B6 deficiency. So you see there, when this B6 deficiency is coupled with folate deficiency and B12 deficiency, it's really detrimental. That leads to a severe kind of anemia and making the individuals completely vulnerable to infections. So there is this particular anemia which is called microcytic anemia, because we do have macrocytic anemia. So microcytic anemia is a characteristic feature of B6 deficiency symptoms. So you see over there the electroencephalogram abnormalities can be confirmed and can be attributed for B6 deficiency. In addition to that, people also suffer from dermatitis. So you see there, dermatitis is inflammation of skin, and then you have glossitis, swollen tongue, inflammation of the tongue, depression and confusion, yes, that can be attributed with the neurologic symptoms, then obvious weakening of immune system. So here we have people can show deficiency system symptoms for a stretched period of time. Initially the people are not even aware about B6 deficiency, but over a period it gets accumulated, and in addition to B complex vitamin deficiency, the deficiency of pyridoxine becomes even more profound. Here we have an example of microcytic anemia. Since B6 deficiency is uncommon, the deficiency of B6 will also predispose this individual to B12 and folate related conditions or deficiency. So you see there what are the risk factors connected with B6 deficiency. The first factor being impaired renal function. What is this impaired renal function? People who already have problems with renal problem, they could be a good candidate for B6 deficiency. And again, people who have problems connected with celiac diseases or autoimmune diseases like Crohn's disease, ulcerative colitis, all these diseases are categorized as malabsorptive autoimmune disorders. So it means what? Your body starts producing antibody against your own cells and destroying their function. So also people who are chronic alcoholics suffer from B6 deficiency. In fact, chronic alcoholics always have variety of deficiency for vitamin B, because most of the time they end up not taking healthy food, and This, over a period of time, puts a stress on their system, making them more susceptible for vitamin deficiency, and especially pyridoxine deficiency is well pronounced in alcoholics. So you see that this is the risk factor that could predispose an individual for B6 deficiency, and we also see the potential applications of B6 in terms of improving the overall well-being of an individual. See, for example, if a person is adequately supplied with vitamin B6 on a regular basis, I mean he could get, or he or she could get sufficient doses of B6, whatever that your body would require in regular quantities, you don't have much diseases connected with the vitamin B6 or pyridoxal. Alternatively, the potential benefits is what we consider as a direct impact on cardiovascular diseases and also an impact on immune related function, and also we have conditions connected with women, especially during pregnancy. The deficiency for pyridoxine can actually have an impact on the growing fetus. So that's one of the reasons why we always insist on giving a balanced diet, and especially not only balanced diet, but the diet should also be enriched with sufficient doses of water soluble vitamins. Yeah, this is a very interesting condition that you need to notice. So people who suffer from B6 deficiency are diagnosed with the peculiar kind of anemia, which is distinguished based on the morphological features. So it's called sideroblastic anemia. Sideroblastic anemia can result from other conditions as well. Suppose if you consider people who take excessive alcohol, okay, they quickly develop sideroblastic anemia. So what is exactly the sideroblastic anemia? It's a kind of microcytic anemia. Normally anemias are categorized looking into the morphological picture of the cells. So here you find a very typical morphology where you have a rounded appearance, okay, for the RBCs, which does not have well developed hemoglobin. So because of well developed hemoglobin, lack of well developed hemoglobin, they are not able to transfer oxygen in the proper way. So this kind of oxygen deprivation over a long period of time could be the direct cause for anemia. Now you look at over there, so 3/4 of the cell is actually lined with the sideroblastic cells. Sideroblastic cells actually is a precursor version of RBCs which do have nucleus, because mature RBCs do not have nucleus. So when RBCs don't have nucleus but are the immediate precursors, what happens is that they basically go further and they stop maturing. So you get a lot of RBCs with still nucleus intact, and the nucleus is not in a position to really make the hemoglobin available for transferring oxygen. So this creates a crisis, and people who suffer from sideroblastic anemia, they suffer from a chronic condition. Very interesting thing to note. So since B6 is the first cofactor in the series where heme synthesis is involved, their lack of participation gives rise to this kind of microcytic anemia, or you could be very specific to say that it's a kind of condition where people lack the ability to transfer oxygen in the proper way. See, there is one more thing you need to notice, although we have seen this earlier. It's basically the antimicrobial therapy. So isoniazid, if you recollect, I have already told about isoniazid that it is a anti-tubercular drug, and it's not given alone. Normally it is given in combination with other 2 or 3 drugs to prevent especially complications connected with drug resistance. very interesting thing to note in this therapy, when people are put on isoniazid over a period of time, because a normal therapy would last from 2 months way back up to 6 months. So even in the first onset, when people start showing anemia, then that's an indication that people might develop certain types of sideroblastic anemia. Okay, so it's directly attributed to isoniazid toxicity. Isoniazid is not only a real good drug for treating tuberculosis, but because of this effect, it also tries to interfere with the functions of pyridoxine. Okay, so end of the day, people are diagnosed with sideroblastic anemia, which is quite different from other kind of anemia, because we do have pernicious anemia, we do have the iron deficiency anemia, but here all other components are available, but still the cell is not in a position to really synthesize heme and perform its function as it has to be. And here you associate isoniazid toxicity playing a direct role or competing with pyridoxine metabolism, thereby making it the a difficult drug to treat. And being aware of this particular condition, it's also reasonable to supplement with pyridoxine for people who are on isoniazid therapy. So this would be a very good practical suggestion to add, because isoniazid still it's a good drug, so you don't want to withdraw from the market. So the next in line would be to look at ways of circumventing this problem. And people have found that taking I would say not only the effective nutrient rich components, but a balanced nutrient rich compound pyridoxine along with other anemia curing vitamins like folic acid, B12 in combination would help treat this condition. See, one more thing we need to consider, because there are certain sideroblastic anemia which could result from leukemic abnormality, or it could be even inherited, probably a genetic mutation. But the one which I am emphasizing here is basically the sideroblastic anemia, which is exclusively vitamin B6 deficiency, and this is basically a reversible condition. So people get it, and once you treat them with sufficient pyridoxine, the conditions can be reversed. So you see that how do we diagnose this condition? They aspirate cells from the bone marrow, they stain them, and they look for these characteristic presentations. So if at all we are going to have such kind of presentation, then that's an indication that the cells are still in the stages of maturation, and eventually they would house all the receptors what you would expect for T cells and B cells would be present. Now one more condition. So this is a condition connected with inflamed skin, and this is seborrheic dermatitis. So what is seborrheic dermatitis? So these oil producing glands of the skin, they are helpful in maintaining the tone of the skin in terms of keeping the skin fresh, and if those cells get inflamed, okay, so we end up in a inflammatory condition. What we tell technically is seborrheic dermatitis. In other words, one version of seborrheic dermatitis is what we call it as the dandruff. Okay, so although dandruff is a universal problem of hyperproliferation of cells, you have this underlying seborrheic dermatitis is the primary cause for such conditions. So here you have especially the scalp, face and chest. We have potential components which can address this inflammatory condition, and the primary being pyridoxine. Yeah, you could use moistening agents, but this condition will not respond to it because it's fundamentally because of vitamin B6 deficiency. So if you look at it, you also have, along with this symptom, seborrheic dermatitis, angular cheilitis. Can you see there? At the junction of the mouth, especially the junction of lips, you find inflammatory spots. So that's quite damaging to look at. Okay, so that's what we call it like cheilitis. Can you recollect at this point any other disease where you have cheilitis symptoms? Yeah, that's true. You would actually look at riboflavin would also be the vitamin, and that deficiency can give rise to angular cheilitis. But pyridoxine deficiency and riboflavin deficiency together can aggravate the condition. So here you have symptoms of seborrheic dermatitis, and here you find again this is a tongue with inflammation. So it's all connected with inflammatory conditions with the smooth muscle, especially the area of mucosal tissue in the oral cavity. So apart from this, people also report neurologic symptoms connected with pyridoxine deficiency. So as I told you in the beginning, somnolence. So this is wakefulness, especially somnolence is wakefulness, and this condition is basically a daytime sleepiness. Okay, it's a condition where people are not alert, they lose energy. The reason is the neurotransmitters biosynthesis directly depend on PLP. So if PLP deficiency is there, the alert neurotransmitters which actually help in the proper functioning of synaptic junction between excitatory neurons are under peril. So here you end up with neuropathy, and this particular condition is what we call it as seizures. So this is quite prominent in adults, what you consider to be the seizures associated with pyridoxine. So for example, if a person is otherwise healthy, he doesn't have a history or inherited condition of seizures, and they don't respond to any therapy all of a sudden, and supplementing with pyridoxine would drastically improve their condition. So this is what the case studies and many of the research reports and clinical reports suggest. So people who have symptoms of neurology or neuropathy without underlying condition, especially if there is a suspicion that it could be pyridoxine, then yes, true, pyridoxine can really take the inflammatory condition to the next level, creating such symptoms. Now we have one more condition, what we call it as pyridoxine dependent epilepsy. See, pyridoxine dependent epilepsy is little different from the adult seizures caused by pyridoxine deficiency. Probably we can also link this as an extension of our body's inability to cope up with stress. So here we have PDE, which is basically a condition exclusively connected with prenatal and neonatal period. So you find children suddenly develop seizures, and they don't have an underlying anomaly, and supplementing with pyridoxine completely reverses the condition. So this kind of disease, the seizures in the neonatal newborn children, is what we consider as pyridoxine dependent epilepsy. So in summary, we can say you have seizures both in the adults and for neonatal, responding very well with pyridoxine therapy. Now we are going to have a quick review on B6. So it's a wonderful, important water soluble vitamin, and it partakes in several metabolic pathways, and we have seen the absorption is passive because once inside the cell it's phosphorylated, and it's the active form is PLP, and right from glycogen to amino acid metabolism and the neurotransmitter production, vitamin B6 plays a very important role. And above all, deficiency can give rise to really serious neurologic complications. So we would you can take down these questions. So what is the metabolic role of pyridoxine, and how the transamination and decarboxylation reactions are catalyzed taking pyridoxine as a cofactor? So this will be your first question in the review. The second one would be what are the different types of deficiency diseases concerned with pyridoxine? And the third question would be classify various symptoms connected with seizures linked with vitamin deficiency. So in other words, what are the kinds of neurologic complications that can result in pyridoxine deficiency? Thank you once again for your attention.